Hello everyone, welcome back to this new video on quick introduction to number theory. In this video, what we're going to do is talk about finite fields. Let me first give you some examples of fields, not just finite, but what is a field. And the prototype of a field is the real numbers, where you have addition, you have a multiplication. Those two are commutative, associative, they have distributive laws. And there are multiplicative inverses. For everything that is not zero, there is a multiplicative inverse. There are more fields, for example, the complex numbers or the rational numbers. Or finite fields are going to be fields like those that are finite. So let me just define what is a field. So a field is a set F with two operations. Operations mean functions from F cross F to F. So for every two little elements of F, say F1 and F2, it produces a new element in F. So the addition of two elements is supposed to be another element of F, and the product of two numbers is also an element of F, such that first of all, plus and times are commutative, associative, and distributive. What this means is that, for example, that A plus B always has to be B plus A, and A times B has to be B times A. Associative means that A plus B plus C is the same as A plus B, and then add C. And distributive means that A times B plus C is the same as A times B plus A times C. Great. And moreover, a field needs two special elements. There's going to be a 0 and a 1 in your field, such that, well, the 1 has the property that 1 times A is A for all elements A in F, and 0 times A, 0 plus A gives you A for all elements A in your field F. And finally, as I said, every non-zero, every element in F except the 0 element has a multiplicative inverse. What that means is that if you have A in F, for all A in F, there is some B in F, such that A times B is the element 1. And we say, in that case, that B is the multiplicative inverse of A. And as I said, the reals, the complex, the rational numbers, all of these are fields that satisfy this. But what we saw in a previous video is that we have another source of fields that gives us finite fields. When we let P be a prime, then we can consider, remember the notation Z mod PZ. This is the set of 0, 1, 2, up to P minus 1 mod P, where there is an addition. Remember that A mod P plus B mod P is A plus B mod P. And similarly, A mod P times B mod P is A times B mod P. So there is an addition and multiplication, because the addition and multiplication are essentially addition and multiplication in the integers. These two are commutative, they're associative, and they are distributive. And again, this is because they are these properties are inherited from plus and times and the integers. And so that is the first property. The second property is that we always have 0 mod p and 1 mod p that satisfy those properties that we wanted, that 1 times a is always congruent to a mod p, and 0 plus a, that is always congruent to a mod p. You can check those if you want. And finally, what we saw is that those things with multiplicative inverses, so when we did this, we looked at what numbers in Z mod M had a multiplicative inverse. We saw that, well, they are those numbers between 0 and P, such that the GCD of A and P is 1. But in this case, since P is prime, any number below P has no common factors with P. So it is every number 1, 2, 3, up to P minus 1 mod P, which is, in fact, all of Z mod PZ except the 0. And all these three properties tell you that Z mod PZ is a field, but with P elements, so it is finite with P elements. So it is a finite field. Great, let's just play around with one of these finite fields. So for example, when P is 7, Z mod PZ is Z mod 7, Z, and this is 0, 1, 2, up to 6 mod 7. And I can add, so 3 plus 4, that is 7, which is 0, modulo 7. I can multiply 3 times 4, that is 12, which is 5, modulo 7. And I can find multiplicative inverses. What is the multiplicative inverse of 3? Well, it will be a number such that is a class, a congruence class, modulo 7, such that 3 times whatever 3 inverse is gives me 1, modulo 7. So what is that number? So 3 times 2 is 6, that's minus 1. So 3 times minus 2, that would give me 1. So if I do 3 times 5, that is 15, which is 1 modulo 7. So 5 is the multiplicative inverse of 3. What about 4? What about 4 inverse? So I'm looking, so I'm trying to find x such that 4x is congruent to 1 modulo 7. And remember, in previous videos, we've actually learned how to solve these methodically. But I can sort of like eyeball it here, that 4 times 2 is 8, and 8 is 1 mod 7. So 4 times 2 is 8 is 1 modulo 7. So 4 inverse is 2 modulo 7. Okay. Very good. Now, what about, so these are fields with P elements, with a prime number of elements. Are there fields that are finite with other number of elements, that is a composite number of elements? So one would try to think of maybe, so let me ask here a question. Are there fields with m elements. And remember that in fact, so let me just write here, a fact is that the set Z mod MZ is a field if and only if M is prime. So if there are such fields, it's not through this construction. However, there are fields with other number of elements. So for example, I'm going to give you a couple of examples of how to build. Here's a field with 9 elements. How I'm going to build that. By the way, a field with q elements, we call it Fm, or a field with m elements would be Fm. So here, what I'm building is F9. So here's a model for F9. F9 can be built as F3 adjoint I. So I'm going to start from F3, where F3 is going to be Z mod 3Z, that we know is a field with 3 elements. And I'm going to adjoin one more element called I, like the I in the complex number, such that I squared is -1. So this is going to be the set of A plus BI, where A and B are going to be elements in Z mod 3, and I is an element is such that I squared is congruent to -1 modulo 3. That's its defining property. So all the elements that are here are 0, 1, and 2 modulo 3, and then 0 plus I, so just I, and 1 plus I, and 2 plus I, and then 2I, and 1 plus 2I, and 2 plus 2I. That's 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. So that's all the elements that are in this set, and they form a field. Let me show you, for example, how do we find the multiplicative inverse of 1 plus I. Addition and multiplication is like in the complex number, so one can show that those two addition and multiplications work, and they are commutative, associative, and distributive. So the question is whether there are multiplicative inverses for all these elements. And I can actually use the same trick we actually find to invert complex numbers. If I want to see what is 1 over 1 plus I can multiply and divide by the complex conjugate of my quantity, and this is 1 minus I divided by the difference of squares here is 1 minus -1, so it's actually 2. So it's 1 minus -1, so this is 1 minus I over 2. But see, 2 in Z mod 3, the inverse of 2 is 2 modulo 3. So the inverse of 2, which is what this denotes, is also 2. So this is the same modulo 3 as 2 times 1 minus I. So this gives me 2 minus 2I, which is, by the way, modulo 3, this is 2 plus I, because -2 is congruent to 1. Okay, so let me check that that works. So what happens if I multiply 1 plus I and 2 plus I? I'm hoping I'm going to get the number 1 back. So if I distribute here, this is 1 times 2 plus 1 times I, and then 2I, and I times I is -1. So I get 2 and -1 gives me 1. And I plus 2I is 3I, but 3I is 0 modulo 3. So I get 1 mod 3. So you see that this tells me that they are multiplicative inverses of each other. So we do have multiplicative inverses, and you can find all the multiplicative inverses for every element. How about a field with 4 elements? So here's an example of a field with 4 elements. Note, let's just check. I already said, but Z mod 4 has 4 elements, but it is not a field. For example, it is not a field because the element 2 mod 4 does not have a multiplicative inverse. Let's check that. So what happens if I do 2 times 0, I get 0, 2 times 1, I get 2, 2 times 2, I get 4, which is 0 mod 4, and 2 times 3, I get 6, which is 2 mod 4. So these are all mod 4, and none of them are 1. So there is no multiplicative inverse. None of 0, 1, 2, or 3 work to multiply by 2 and get 1. So this is not a field. So instead, what we do is we start from F2, which is Z mod 2Z, and then I'm going to build F4 as Z mod 2Z, adjoined something that I'm going to call, let's call it X, such that x squared plus x plus 1 is congruent to 0 modulo 2. Okay, so what does that mean? This is elements a plus bx, such that a and b are in F2, so they're just, the coefficients are just modulo 2, and x has that property. Okay, so what turns out to be is that this element or this field is just a field with 0, 1, x, and 1 plus x. Those are all the elements. And you can multiply elements. So x times 1 gives you x. How much is, or you can add elements, x plus 1 plus x. What is that? That is 1 plus 2x. And 2x is 0, so this is just 1. How much is x times 1 plus x? X times 1 plus x is x plus x squared. But you see, x squared plus x plus 1 is 0. So that means that actually x squared plus x is congruent to minus 1, which modulo 2 is just congruent to 1. So this is actually just congruent to 1 modulo 2. This, by the way, tells you that the inverse of x in this field is precisely 1 plus x. So you see that every non-zero element, the inverse of 1 is 1. The inverse of x is 1 plus x, and the inverse of 1 plus x is x. So everything that is non-zero has a multiplicative inverse. So here we do have a field. Okay. Next, in the next video, we're going to be talking about the multiplicative order of a number and Fermat's little theorem. See you then.